Okay, now I think it's the record is started. Okay, Sarah, thank you. Then I can proceed. Yes, I I'm asking again. It's everything. It's like that. Every time it's like that with Teams. Can you hear me and can you see my screen?
Yeah.
Okay. Hello, everyone, again. And as I said, today is the third day of our workshop. I will talk about the energy conversion part. Yes. I will start with a small the contents of our presentation today, of our workshop. I will start with a short biography, my biography, and after I will talk about the wind turbines and power curves. Yes, it's a review because I think that you saw this in the last days. Yes, mainly in the lecture of Sarah. Yes, and she talked about the wind turbines. You did exercises about that, and just this small review of the main points that are interesting are important for our part. Yes. After we'll talk about the type of generators and the characteristics, and then the electrical generators. After, we will talk about the wind energy conversion systems and the topologies, the commercial topologies employed and taking a look for the offshore market. Yes. I will show some manufacturers, and after the power converters, the grid integration, and the grid compliance. And as you can see, the agenda it's wide, yes, and so I will try to explain the basics of each topic. Of course, if with a lecture of some hours, it's impossible to go very deep inside, and also some topics need some deep acknowledgements about the electrical parts. And then it, as our workshop is proposed, is more like the basics, uh, the, the basic things to understand the operation and the of the wind energy conversion systems. Yes, and I will propose to you maybe a different um, the dynamic of this presentation. It's I will do this more like a lecture, like a class, not like a speech. Yes, I want to say that in a speech we I talked, and after are the questions. But I'm proposing to you to do like a class. Then I will talk. I will show the slides. I will discuss the tema with you, and you can ask, just raise the hands. I can see here I have two screens. Sometimes I'm looking in this direction because I'm looking for the screen that my presentation is. And but you can raise the hands and make questions. You can do commentaries. It's very interesting if we can share some experiences, and I can share my experience with you also. Then, um, um, I am. I think I I did not say that I'm Professor Victor. Yes, I am professor at the Department of Electrical Engineering of UFMG, Federal University of Minas Gerais. Yes. My titles, yes, my studies my master study and my doctoral were in electrical engineer. Yes, and both at UFMG, and part of my doctor was in the TU Dresden in Germany. And both in master and doctor, I studied the wind systems, and so I work with this topic more than uh, I think today 15 or 16 years that I work with wind systems. Yes. Also, I just finished my postdoctoral at Laplace in laboratory in France. And I am also coordinator of the post-graduation program in renewables energies here at UFMG. Yes, a especialização em energias renováveis. I am uh, I'm very interested in the renewables energy, and I'm always looking for spread the acknowledgements about the energy, the use of the energy sources, of course, in the view of the electrical engineering. Yes, my main interest areas that my research are in wind and photovoltaics energy conversion systems and power electronics application in these systems. Thus, then I don't work with the energy source, as I can say, but with the energy conversion system as the electrical part of the system. So, as I said, we'll talk about the turbine power curves, yes, and you know that the turbines have a CP, yes, the power coefficient. The power coefficient is dependent of the wind speed, of the rotational speed, and also of the pitch angle and the angle of the blades. Yes, and here we can see two examples of power curves, not power curves, but efficient curves of different turbines. Here we have a small power turbine, a 10 kilowatts turbine, and we can see here the change of the efficiency according to the pitch angle. Yes, in this case, it's a small turbine. The minimum angle is 15 degrees. The efficiency is not very, the efficiency is low. It's around 20% in the maximum point here. Yeah. Here in the right side, we have some turbines of commercial turbines between 1.5 mega and 4 mega. Yeah? And we can see here that the maximum power coefficient can reach almost 15%. In these days, it's common to have efficiency more than 15%. Yes, and we can see also the change of the power of the power coefficient characteristic according to the pitch angle. Yes, and also we can see the behavior of the power coefficient according to the tip speed ratio. The tip speed ratio is a ratio between the rotational speed and the wind speed. And we can see here that even for a small or a high power turbine, the characteristics are similar. Of course, the values are different. Yes, we can see here the range of the tip speed ratio. It's until 9. Here we go until 20. But the characteristic is always the same. The power, the efficiency, it's increased. It increased until maximum point, and also and after it drops. And always you can see that we have a maximum efficient for each pitch angle. Yes. Of course, most of the times we are interested in work with the maximum efficiency. Yes, you can ask, Kelvin.
Hi, wouldn't CP be an intrinsic property of the wind turbine and not depend on external quantities like velocity?
I could not understand you. Can you talk a little louder?
Yes. So, wouldn't CP be an intrinsic property of the wind turbine, like a manufacturing property, and not depend on the velocities, like an external quantity? Like
No, no, you are partially correct. The CP characteristic, I can say the curves of the CP we see here for a 10 kilowatts and for megawatt system, the characteristics of the CP are depending of the design. Yes, in the aerodynamics of the blades, for example, determines the CP characteristic, the curves. But the CP is not fixed. It depends of the rotational speed, the wind speed, and also of the pitch angle. And then it can change. This is not fixed. The behavior can change with the operation of the turbine. Can you understand?
yes, thanks.
Yes, it's like that. It's the characteristic, it's dependent of the aerodynamics, but the CP can change. Okay. So this this CP characteristic of the turbines, this can be utilized to calculate the power of the turbine. Yes, and the power converted by the turbine, it's dependent of the radius of the turbine, of the wind speed. We have a power of 3 of the wind speed and also of the CP. Yes, and so in this graph here, I fixed I fixed my pitch angle to uh, the minimal angle. Yes, 0 degrees. It's I choose to do this because I want to work with the maximum possible efficiency of the system. Uh, I changed here. Look to graph. Can you see my I forgot the name of my. Is it possible to see your mouse? Okay, thank you. I can see here that I changed this graph. It's the turbine power according to the turbine speed in rotations per minute. Yes, and I changed the wind speed. And we see here 11, 9 meters per second, 7 meters per second. And here we can see the power characteristics of the turbine. Yes, and for example, if we have a wind of 11 meters per second, the maximum point, the maximum power that can be reached by this turbine is 4 megawatts. Yes, 4 megawatts. It's the maximum power for 11 meters per second. Yes. Um, this is for my example, the rated wind speed, and then the rated speed of a turbine. It's the wind speed that in the maximum point to the turbine to operate with the rated power 4 megawatts in this case. In this example, we can see here the maximum for megawatts. If we change the speed of the wind, of course, the power will change. Yes. And also, what is 4 megawatts? In this curve, we can see that the maximum uh, um, uh, is wind speed. It's 11 meters per second. But the wind, it can be higher than this. We can have 12 meters per second. We can have 13 meters per second. Yes, and what means higher powers. But when we say rated power of the turbine, we in fact we are talking about the rated power of the generator. In this case, the generator is designed for 4 megawatts, and then the rated speed is 11 meters per second. Another turbine, I can have 5 megawatts with a rated wind speed of 12 meters per second. This is a design. This is the product choice. Then the turbine will be chosen. We will be choose to a specific site. Well, then I have an offshore site with higher speeds, or an onshore site with smaller wind speeds. Then the turbine will be chosen for these characteristics. This is, I will not talk about this. We have all other lectures to address this choice. Yes, as I can show you is the power characteristic. The power characteristic is the maximum power is in this case in the rated wind speed of 11 meters per second. We have a generator with a 4 megawatts system. And it's important to see, even, for example, if we have here a wind speed of 9 meters per second, the power characteristic of the turbine, it's a curve. This curve, it's linked to the CP. Then the maximum power here, or here, it's always in this maximum point of CP here, of the efficiency of the system. That means that the rotational speed of the turbine can change the power of the turbine. And by mistake, several people thinks that the speed of the turbine is determined by the wind speed. For example, it's quite obvious to think if I increase the wind from 9 to 11 meters per second, it's quite obvious that the turbine speed will increase. But this is wrong, because the turbine rotational speed, is defined by the electrical part, not by the mechanical part. Yes, and this is very important to us to understand. Yes, it's necessary to have a control system to permit the turbine to operate in the maximum power point. Yes, is this yellow curve here that I signal as CP max, that this curve cross the maximum points of the power curves. And so it's important, again, The speed of the turbine is imposed by the electrical generator. It means that it can change according to the control system, not according to the wind speed. Of course, the wind speed will it's information to calculate this rotational speed. And so another information is the pitch angle, the mechanical control is used mainly for power limitation. Let me see. Oh, I forgot to put a curve here, but I try to explain. Yes, it means when I have the rated wind speed 11 meters per second and winds is smaller than the rated wind speed, I will try to control the system to reach the maximum efficiency. Yes. But the wind changes. I can have, for example, 12 meters per second, 15 meters per second. But the power is limited by the generator. If I have a generator of 4 megawatts, it cannot generate 5 megawatts or 6 megawatts because it's not possible to do this. And then for wind speeds higher than the rated wind speeds, I will do a mechanical control, the pitch angle control, in such way that with the mechanical control, I decrease the efficiency of the turbine to limit the power. So I will talk a little more about this some slides ahead, but it's clear that we have two controls in the turbine. We have a electrical control below the rated wind speed to reach the maximum power, the maximum efficiency. But above the rated speed, I will do a mechanical control to limit this power. Questions? Of course, you saw in other lectures that the turbine, yes, back into this power here, to this power equation, the radius it's linked to the power. Cesar?
Okay, thank you, Professor. If you have a wind speed higher than the wind speed rated that you present here,
you do a mechanical control. Yes, the pitch angle control. If I have, in this example, 12 meters per second, I will start to control the blades to reduce the efficiency of the system, then to limit the power for 4 megawatts. I cannot generate more than rated power.
Okay, I understand.
Okay?
I understand. But considering this picture, the power coefficient still remains the maximum after this speed? No.
No. Yes. We can back we back here. This power coefficient is maximum until in these points here, until the rated wind speed, And when I control the pitch angle, I will increase the pitch angle, then I will change in the CP curves. I will decrease the efficiency. Then in wind speeds above the rated speed, I will not work with the CP max, with the maximum efficiency. I work with smaller efficiency.
Okay, so we have basically two zones or two regions in the operating wind turbines. First, a second region. Let's talk about the second region. Is the region in which the optimization zone, in which the pitch angle is equal to 0, and the third region is when we have a pitch regulated systems to regulate the speed using the pitch angle. Am I correct?
Exactly. I am trying to. Yes, I was looking
Yes,
for
that's
this
it.
curve. Yes, this curve we have power according to the wind speed. Yes, and then I explain this now. We have a cut in wind speed. That means the speed below the cut-in wind speed, the system does not generate power. Yes, and so the power is 0. Between the cut-in wind speed and the rated wind speed, we work with power maximization. For the power maximization, we have a electrical control. The electrical control do what? It varies the rotational speed to reach the maximum power point, the maximum efficiency of the turbine. Above the rated wind speed, I cannot have powers more than rated power. And then in the rated wind speed, I have the rated power. For winds greater than this, than the rated wind speed, I will do a power limitation strategy. This strategy is a mechanical control, is the control of the angles of the blades. In this case here, we have a constant rotational speed, which means that we don't work with the maximum power. We are decreasing the efficiency of the turbine to limit the power. And then when we see here that the power is limited to the rated power. And then I can have winds much more higher than the rated speed. Yes, and in a zone that the winds are, I can say, it's controllable with the mechanical pitch, I can limit the power. But for example, the turbine can be rated by very high winds. For example, a tornado or a hurricane. Oops. Can you hear me?
Yeah, I'm listening to you.
Yes.
I had a problem here. I don't know
I
what
think
happened.
your camera has frozen.
Hear you. We can hear you.
Just 1 minute. I had some problem in the. My computer is blocked. I don't know why.
Is it possible to hear you now?
Your voice is okay, but your image is frozen.
Yes, but the computer, I cannot change the presentation. I can I will try to restart the computer, sorry. Oh. I, believe it or not, the Windows starts to update during the presentation. Then I try to come back.
What happened?
This never happen. I never know. I cannot say this. It is always happen. Yeah.
Yeah.
And then coming
This
back
is one of
here.
Murphy's laws.
Yes. Coming back in, it's good because we have some time, yes, but I try to hurry a bit here. And as I saw, we have two regions of operation. Between the cutting speed and the rated speed, we have the power maximization, we have an electrical control. In the second zone, we have a power limitation. Then
Victor,
I have,
the presentation is not showing.
oh, sorry. Thank you.
Okay.
Okay,
No,
okay.
that's
Thank you.
okay.
Yeah,
Yes.
thanks.
And then we have between the cutting speed and the rated speed, electrical control, power maximization. Between the rated speed and the cut out speed, wind speed, we have the power limitation, we have the pitch control. Above the cut out wind speed, the cut out wind speeds are speeds very high, for example, a tornado, a hurricane, that can damage the turbine, the blades, and then the system is turned off. Yes, and it's kind of a protection of the system. Okay, but even above the rated wind speed, we can operate, but with the limitation done by the pitch angles. Paulo,
Yes. Just to try to see if I understood it correctly. You said that above the rated speed, there is a mechanical control, which is turning the angle of the blades, the pitch angle, which
Yes,
I
exactly.
understand is controlled by the turbine control system. So you change the angle to change the efficiency and make a limit on the power. Okay,
Exactly.
that is clear. Then below, you talk about electrical control below the rated speed. So does this electrical control also generate some mechanical actions on the turbine?
Yes, the rate or the rotational speed. Yes, the control is electric in the electric generator, and the action is to change the rotational speed. Yes, the objective of the electrical control is come back in here. Here we are changing the rotational speed to reach the maximum efficiency. Okay?
So it is a mechanical action changing the rotational speed. So you're
Speed.
okay.
The action of the electrical control is to change the rotational speed, the mechanical.
So probably taking an action on gearbox or something mechanical inside the turbine to do that.
I could not understand. I could not hear you. Can you repeat, please?
I mean, probably taking an action on the gearbox or something else to change the rotational speed and not by the wind.
No, nope. The gearbox is fixed. It's electrical control. Take care. It's very important. It's electrical control. We'll see after how this electrical control is done. I just want to that you understand that the speed of the turbine it's not imposed by the mechanical part, but it is imposed by the electrical part, by the electrical generator. Okay?
So now clear. Let's wait for the moment.
Yes. And then we see here that the power curve no, but the power it's dependent of the radius of the turbine. Yes, and for offshore applications, we are talking about bases of offshore, and we talk about the onshore and also to look to the offshore also. And we can see here an evolution of the turbines, yes, and for the bigger the turbines, yeah, the radius of the turbines of the blades, higher powers, but the power is defined by the electrical generator. For onshore wind farms, yes, we have here in this moment the medium power of installed wind turbines onshore is 3.5 megawatts. For offshore turbines, we have higher powers, yes, and we have for the onshore market we have commercial turbines available between 4 or 5 megawatts, and for offshore we have higher power turbines. Yes, we have nowadays 12, 13, we have a prototype of 15 megawatts from GE, yes? And higher powers mean new technology changes, challenges, yes? We have the problem first of design of the blades that we saw yesterday, yes? Bigger turbines, problems of materials, and also we have problems, not problems, but challenges in the electrical part. I need higher power generators. I have um, connection systems to the grid with higher powers. And so we will see here in my presentation here, this evolution in the challenges and the development of technologies for higher power means offshore applications. And so just to take a look in the system, so we have the blades, as we are already said. The blades, they can change the pitch angle to do a power limitation. Yes. The turbine converts the kinetic energy of the wind in mechanical rotational speed. That means mechanical energy. This mechanical energy goes to the generator. We can have a gearbox or not, depends on the technology, we see this. But the generator do the conversion of the mechanical energy to the electrical energy. Yes, we have a controller to do this. Yes, we have a controller to electrical part and also to the mechanical part, and also to change the nacelle and all other controls of the turbine. We are interested here in the generator and the connection to the grid, the conversion of mechanical energy in electrical energy. We have three types of generators, of electrical generators applied in turbines. DC generators, this is just for small turbines, mainly isolated applications with batteries, and then it's not of interest for us. It's for small powers, isolated. For electrical energy production, to feed in the grid, we have synchronous generators and asynchronous generators. The synchronous generators are divided in two types. One rotor, or field current excitation, that it's generators similar to the conventional hydro generators applied in hydro power plants. Of course, it's similar, it's not equal. And when we have a hydro power plant, we have a generator generally with field current excitation. And then the generator is similar for the wind turbines application. We have also permanent magnetic synchronous generator. Yeah? The technology in expansion and very attractive for offshore applications. And we have also the asynchronous generator, also known as induction generators. The induction generators can be two also. The one rotor, one of the main technologies applied to wind turbines, and a squirrel cage rotor. The squirrel cage rotor are the machines very used in industry. And I mean in industry, mining industry, processing industry, in general industry, we use squirrel cage industrial machines. We have some applications of these for wind turbines, but it's not very spread. I will talk a little more about each one of these generators and their characteristics. Cesar?
Professor, just a terminology doubt. In literature, we have electrically excited generator.
Yes,
Electrically excited generator is the same thing as wound rotor.
exactly. Yes, it's one rotor. It's electrically excited. It's a more common name for the generators. Yes, one means in Portuguese rotor bobinado with coils in the rotor. Okay. Then characteristics of synchronous generators. This is very electric. I will try to explain for you. Of course, some technologies, some explanations are very hard to do here, but I'll try to explain for you the basics. Yes. The synchronous generators have the speed determined by the number of poles and the frequency of the supply. Let's explain that. As I said, the turbine speed, rotational speed, is determined by the generator speed. And so, for the synchronous machines, the mechanical speed, the rotational speed, is dependent of the poles and the source that the generator is connected. What means poles? Here we can see a wound rotor machine. Yes, a wound rotor machine. This machine is a machine that we have coils here in the rotor. Each one of these structures here that you see, it's a pole. A north pole, a south pole, north pole, south pole. We can see here several poles for this machine. Here we have a permanent magnet machine. The blue ones are the north, the south are the red ones. And we can see here that this machine has 6 poles. North, south, north, south, north, south. It's just the magnetic flux that is produced for the operation of this machine. And then the number of the poles, the construction of the machine determines the mechanical speed. Also, the electrical connection to the grid or to the source. Here we have the stator of this machine. The stator is where the energy, the electrical energy is produced. We can see that like that. Then the stator, we have the flux of electrical engine, of electrical energy. Yes, and the connection of this stator is, for example, to the grid. Yes, and then this frequency of the supply, or frequency of the grid, for example, determines also the mechanical speed. Characteristic of the synchronous generators. high number of poles can be constructed. We see here several poles. For wind applications, we have 100 poles. It's possible. And what's the advantage to have high number of poles? Possibility of direct connection to the wind turbine. We see here by the mechanical curves that the speed of this kind of turbine is small, around 15 rotations per minute. When you use a machine with high number of poles, I can avoid the gearbox. I can have a connection directly from the turbine to the generator. This is called gearless technology. But one characteristic of the synchronous generator that it's impossible to connect directly to the grid for wind applications. Why? The wind speed changes. So the turbine and generator speed, it's prone to change. But the synchronous speed, the synchronous generator, it's designed to operate in a fixed speed for a fixed supply. Then the direct connection to the grid, it's not possible. But we use synchronous generator. And you see how you can use this. Power converters are necessary. I always have the generator, the synchronous generator combined with power electronics or power converters. Advantage of permanent magnetic synchronous generator. It's one of the main technologies in expansion worldwide. Yes, the high number of poles permits the direct connection to the wind turbine. Yes, so it's gearless. What means a system gearless? One less component. We don't have the gearbox. It's a component with mechanical fragilities. It's necessary maintenance, constant maintenance, and if we avoid the gearbox, it's very good. It's not necessary to supply the rotor. And if you don't have currents in the rotor, but the use of permanent magnet, no rotor currents, so no rotor electrical losses. And then permanent magnetic synchronous generator are with high efficiency. They have high efficiency. The disadvantages are the cost is still high, but decreasing. Yeah, for offshore applications, the expansion it's makes the cost decreasing, and the permanent magnet can be demagnetized by temperature or electric failures, mainly for by the temperatures. Overheating of the machine can destroy the machine and can demagnetize the permanent magnet. What means if one permanent magnet is demagnetized, the generator is useless. It's necessary to disassembly and construct again for it, so it's maintained. It's very complicated. Alvin?
Hi, what's the reason for the high efficiency of permanent magnets? And also, I think Sarah mentioned about the high heavy metals which would be required for making the permanent magnets, which should be a source of concern.
Yes, yes. The permanent magnetic are hard earth. It's kind of specific materials. Yes. I don't know exactly the name in English. Neodymium, ferro boron, and also another technology. It's called hard earth because they are they are metals that are hard to find in the nature. And also it's a process of doing the permanent magnetic. This is a process with high environmental aspects. It's I can say it's not a very how can I say this, with high impacts. It's necessary high energy. It produces it produces pollution. Yeah, and also China has the technology. And so most of the permanent magnet in the world is sold by China. And they are not very worried about environmental. And also this cash of the concerns about the permanent magnetic. But it's one of the technologies that it's increasing very fast. Yes, for offshore applications, it's the system more used. Cesar?
As you said, a permanent magnet can be demagnetized. So in such generators, synchronous generators, we have a cooling system. I have a question. The cooling system is to cool the magnets or to cool the high temperature or winding?
Oh, the cooling system is for the whole machine. Yes, and it's okay. There is different types of cooling systems. We have systems with cooled by wind. Yes,
Wind, water.
and also, but it's not uncommon to have systems cooled by water, just to avoid this kind of problems.
And another question to you, Professor. I know, as you presented here, there's an equation to correlate the number of poles to the synchronous generators and the speed of the generator. Therefore, the number of poles in double fed induction generation is eventually four or five poles. No?
We will see this next.
Yes. I would like to know, as I asked to Sarah yesterday, sorry, on Monday, as I asked to her, how many poles are inserted on direct drive permanent magnet generators? Do you have a
100. Between 80 to 100. It's a huge amount of poles, and this is a complication of this machine. The cost of this machine is still high. Yes, and we also have problems because machine with a high number of poles are machines very big. Yes, we avoid the gearbox, but we need a machine with special constructions.
Okay, okay. Thanks so much.
The induction generator, it's not very used for traditional generation systems, thermal generators, but they are used for wind turbines. Yes. The speed, it's also determined by the number of flow and the frequency of the supply, but it can vary according to the mechanical power. What this we call sleep. The sleep, here we can see in the left side the rotor one this machine. We have aluminum bars, and we don't have supply to the rotor. As the name said, it's the currents in the rotor flows by induction. As we have aluminum bars, this is very simple to construct and very, the maintenance of this is almost free of maintenance. And in the right side here, we have a curve, a torque, it's a power also, curve of the induction generator. Here, when we have zero electrical power, we have the synchronous speed. We see here that the synchronous speed is exactly the same of the synchronous generator. Depends of the number of poles and the frequency of the supply. The difference between synchronous and asynchronous generator, the synchronous just work in the synchronous speed. The induction generator just work outside the synchronous speed. We see here the following. Below the synchronous speed, we have operation as a motor. It's not our case. Above the synchronous speed, we have the operation as a generator. And higher the speed, higher the electric energy produced by the generator. But the region of operation of this machine is just, it's not a wide range. It's a small range of variation of speed. Some rotations per minute. Another characteristic of the induction machines, we have 4, maximum 6 poles, as Cesar said. That means that when you use induction generators, we need a gearbox. This is mandatory. We need a gearbox when using induction generators. When using synchronous, we can have or not gearbox. Here we see the characteristic of squirrel cage machines. As we said, I said, we have a small variation of speed. This variation makes a huge difference for the operation of the system. Another technology of induction generators is the wound rotor machine. Different from the previous one, where we have aluminum bars here and no supply to the rotor. Here we have coils and we feed current to these coils. So we need a special structure to supply these coils that it's rotating with the machine. If the machine is rotation, we have the slip rings and the brushes to make the contact between the stationary of the machine with the rotationary part, the stator and the rotor. And the slip ring and the brushes, it's a problem because it's very prone to maintenance. At least once a year, it's necessary to change the brushes. And imagine on a tower of 100 meters to go there, to change the brushes, to stop the machine, and imagine for offshore applications. This is a bit complicated. And the maintenance of this kind of machine, it's a concern about it. The difference between the wound rotor and the squirrel cage is applying voltage to the rotor. It's possible to change the power characteristics of the machine, of the generator. This is a simple example when where I changed the rotor voltage, and we see here the black one, it's zero voltage in the rotor, which means the previous case, the squirrel case. As we saw in the synchronous speed, no power. Increasing the speed above the synchronous speed, we have generation. But when we apply voltage to the rotor, I change the power characteristic. And so, while a squirrel cage machine permits a small range of variation of power for a fixed supply, the wound rotor permits a wider speed variation. And this is an advantage for the system. Okay, so for wind applications. So the characteristic, I know that sometimes I know that maybe most of you do not understand very much this type of curves, but I just want to show you the characteristic of each generator. And so we saw the characteristic of the synchronous generators and the main characteristic of the induction generators. Higher speeds means higher numbers of poles, yes, and so it's necessary a gearbox for turbine connection, and so we have always a use of gearbox when using this type of machine. Slip rings are needed for one machines, so increased maintenance. One characteristic of induction generators, they always consumes reactive power for operation. No matter if we are working as a motor or working as a generator, what's the difference between motor and generator? Motor, I am converting electrical energy and mechanical energy. The generator is our case. I am converting the mechanical energy in electrical energy. No matter the operation, induction machines always consume reactive power, always. The speed variation according to the mechanical power permits its connection direct to the grid. Então, so the induction generator, they have some characteristics that it's good for connection direct to the grid. questions, Alvin?
Hi, roughly what fraction of the power is being consumed by the rotor supply?
Uh, can you repeat, please?
Yes, so roughly what fraction of the power is consumed by the reactive power for operation?
Oh, it's a question that we have to pay attention. Reactive power, it's different, it's not energy, which means I cannot answer what's the fraction of energy that it's consumed by reactive power, because reactive power, it's not energy. Yes, energy, electrical energy, it's linked to the active power. I am the mechanical part, the mechanical conversion wind energy in electrical energy. This is active power. The reactive power is just currents that are flowing for the machine, but it does not represent energy. The problem of the reactive power, when we have reactive power, we have increased losses in the grid, in the generator. It's clear?
So is the rotor being supplied by the wind turbine itself?
No.
The power,
the reactive power is supplied by the grid, not by the turbine, because it's not energy. Okay?
Okay.
This is a good question. Huh? And what's the problem of consuming reactive power? The grid has to supply this reactive power for the operation of the generator. And this can be a problem for the grid. It's not a problem, but we can see it as a drawback of the grid. Clear, Alvin?
Yeah, it's clear. Thank you.
More questions about the generator part? So I go ahead. In some minutes, we can make a break. Yes, but let's continue a little bit. The induction generator was where the first technology used for wind energy conversion system. This is called Danish wind turbine, Danish concept.
Danish concept.
Danish concept. Yeah. The Danish concept, we have the turbine, a squirrel cage induction generator. Always, if I have an induction generator, I need a gearbox. It's mandatory. Okay? One problem of induction generators is the starting of this machine. So the wind can change. And in some time I have zero wind, and the system is turned off. And after a while, the wind will increase above the cutting speed, and the system will start to operate. What means the generator will be connected to the grid and start to operate. But during this connection to the grid, we have some a starting problem that induction generators produce high currents during its connection to the grid, during its start. High currents, I mean currents much higher than the normal currents of these machines. And this is bad for the machine, and this is bad for the power system. So it's necessary a system to help the start of the system. We call this soft starter. The soft starters is a system, electronic system that will help the system to start softer. As we said, induction generator consumes reactive power, and so as Alvin asked, who will supply this reactive power? The grid, or we can use capacitors to do this supply of reactive power. And always for this direct connection to the grid, we use capacitor banks to power factor correction, yes, to supply the reactive power for this machine. So this technology, necessity of gearbox, necessity of a software starter, capacitors for power correction, and also lower efficiency of conversion. It's not the lower efficiency of the generator, but the lower efficiency of the wind energy conversion. We see here again the power curves of the wind. The colored ones here are the power curves for different wind speeds, 11, 10, 8, and so on. The black one is the generator operation, which means the operation of the system, of the turbine, it's determined by the crossing between the generator and the turbine curves. Okay? So, as I said previously, the speed is determined by the generator. In this case here, we see where the power produced by the generator plus turbine. If I look here, the 8 meters per second, this point here is the point of power. The generator is generating this power. It's converting this power of the turbine. But look the maximum of this curve, where is? We have a difference between the real operation and the maximum possible operation, which means part of the energy it's not converted in electrical energy. It's kind of losses. I am not extracting all the energy that the wind can deliver. Smaller the wind speed, higher is the difference between the real operation and the maximum operation. There is some concepts to make this power extraction better, but always I have part of the energy of the wind not converted in electrical in energy. And because of this, we say that the use of this concept has low efficiency. It's called fixed speed systems. So we see that the speed is imposed by the generator, and the turbine will work with a fixed speed. The gearbox is also fixed. This is very important. There is no, it's not commercial available a wind gearbox, a gearbox for wind applications that can change the gears. In fact, I have seen some years ago one technology from Voigt, it's a company with a variable gearbox, but it's just a concept, not wide spread, because it's very hard to build a gearbox with variable gears for this kind of applications. Then, if I have an induction generator directly connected to the grid, we have a fixed speed operation, loss in the power. Clear these questions?
Clear?
An evolution of this old technology. Just explain this, yes, and this technology was the first ones. This nowadays is just used for small power applications. I have saw some research about employing this kind of system for offshore applications, mainly because of the robustness of the skewer cage generator. Yes, but as we have here a gearbox and we have some more problems for the grid connection, it's not a very spread technology for offshore applications. Nowadays, they are just used for small power turbines or some small systems. An evolution of this fixed speed system, it's called variable speed or partial variable speed system. In fact, I don't like this name because for me it's still a fixed speed system, because the variation of the speed it's very short, and then we have small efficiency also. In this case, wound rotor induction generator are used. If you have induction generators, we need a gearbox. This wound rotor is directly connected to the grid. Again, we need a software starter for the starting of operation and a capacitor for power power factor correction, what means to supply reactive power to the system. The difference between this and the previous one is, as we have a wound rotor, we have variable resistance in this rotor that permits a wider variation of speed. But this variation, it's not enough to reach the maximum point. Because of this, that I classify this technology as fixed also. This technology is used in some power plants in Brazil, but also have low efficiency. Also, I have seen some studies to offshore applications, but this is worse than the previous one. In this, the problems worse no, the contrary. This is a bit better than the previous one because we can have these resistances make the system more, how can I say, the impact of the system for the grid. Yes, the start and the reactive power. It's a bit different of the previous one, but still we have problems mainly for the construction of high power generators. It's very hard to construct wound rotor induction generators with powers higher than 4 or 5 megawatts. And then this makes this technology not very used for offshore, and even for onshore we have some applications, but it's not very spread. Paulo?
If we Victor can talk about improvement, some improvement compared to the other one, do we have an idea of how much we can improve from this to the other one?
In terms of energy?
Yes, in terms of improvement in losses.
In fact, we have no improvements in energy because we use here resistances. Resistances, we are increasing the losses. This is not, the efficiency is not lower than the previous one, because even if I have the resistance here, I increase the losses, but this is compensated by a smaller increase in the production of the turbine. This curve here is not straight like that. This has a small slope here, but globally, it's not very interesting in terms of energy. I can say that the efficiency of both are the same. The improvements comes mainly for the mechanical part. This system here, it's, how can I say this, is the stresses of the gearbox are attenuated by these resistances, and so the gearbox it's less stressed than the previous one. And also of the grid side, the use of this resistance here makes this technology a bit more interesting dynamically for the grid connection. And so the improvements are not of energy produced, but for operation of the system. Okay?
Okay, thanks, clear.
More questions? Today, and for offshore applications, the modern wind energy conversion systems apply variable speed systems. The objective is to reach the maximum efficiency for each wind speed. Okay? But let's go back to the generators. The speed of the generators are defined by the number of poles and the electrical frequency of the supply. In the fixed speed systems, this one and this one, the frequency is imposed by the power system, is imposed by the grid. In Brazil, 60 hertz. Because of this, we have fixed speed. The number of poles of the machine cannot be changed. This is the design of the generator. Each generator has their number of poles. So the only way to change the speed of the machine, of the generator, is to change the frequency of the supply. I cannot, of course, I cannot change the frequency of the grid, but I can use power converters to supply, to connect the generators to the grid. And the key of the variable speed systems are it's the employment of power converters. It's necessary to have power converters to make the generator speed to change, reaching the maximum efficiency of conversion between wind and electrical and energy. So the next slides, I will show you the technologies for variable speed systems. I am talking for more than 1 hour and a half, and so I propose you 10 minutes break, and we come back 10:50. Okay?
Okay.
Okay.
So see you in some minutes.
Okay.
So I'm back. Let's start. Emerson, do you want to know to do a question?
No, no, sorry.
Okay. So we see two concepts of technologies: the fixed speed one and the variable speed one. Yes, the modern wind energy conversion system, especially for offshore applications, use variable speed. As I said, the generator must be connected to the grid using power converters. The idea is we have the wind turbine, variable rotation, yes, and again, the variable rotation is defined by the generator. The gearbox is optional. The gearbox is fixed. The gearbox does not play a role in the variation of speed. Okay, the variation of speed comes from the generator. But to work with variable speed, it's necessary that this generator work with a variable voltage, amplitude, and frequency. If the voltage and frequency is variable, this is not possible to connect direct to the grid, because the grid has constant voltage, amplitude, and frequency. The objective of the power converter is convert this voltage. We can say like that. We convert the variable voltage, amplitude, and frequency to a constant voltage, amplitude, and frequency to feed the electrical energy to the grid. And so we come back to the curve of power according to the wind speed. In fact, we explained this curve previously as the power maximization here for the electrical control, but this control is just possible in variable speed systems. The objective is to reach the maximum power point extraction. And for this, it's necessary the use of power converters. Above the rated wind speed, we have the mechanical control. So we see that we have different controls in the whole system: electrical control and the mechanical control. The mechanical control is just to limit the power delivered to the generator. So we have different topology, different concepts of variable speed. The first one is the doubly fed induction generator, widely known by DFIG. The DFIG, it's an induction generator with a wound rotor, also known as doubly fed induction generator. It means that we have a supply in the stator and a supply in the rotor. If we have an induction generator, we need a gearbox. The power converter in this technology is connected to the rotor, while the stator is connected directly to the grid. This is the most used technology worldwide for offshore applications. 80% of all onshore applications use this doubly fed induction generator. When you look the whole installations, 50% is from doubly fed induction generator. So it's widely spread, this technology, because it has the advantage of low power of the power converter. The power converter, it has between 25 and 30% of the power of the machine. What means that? If we have here, for example, a generator of 10 megawatts, these power converters process just around 3 megawatts of power, which means lower cost. The power electronics is one of the systems of the wind energy conversion system that plays the most of the costs. The cost of the power converter in traditional can reach almost 30% of the whole system. And so when we have low power converters, this means lower cost. But the disadvantage, the use of the gearbox and the use of slip rings and brushes, high maintenance. The doubly fed is characterized by a technology with smaller initial costs, but the cost during the life of the system is increased because of the maintenance. High challenges for high power offshore applications. The maintenance is always a problem for offshore. The maintenance, the cost of maintenance for the offshore, it's much more high than in the onshore applications. So this technology, it can be applied for offshore applications, but we have some challenges. It's under development what we call brushless DFIG. The brushless DFIG, it's a generator with less maintenance, but is still just research. We have no high power systems and operation. So the doubly fed, it's very largely spread in onshore applications. For offshore, it can be used, but it's not the preferable technology. The squirrel cage induction generator with full converter, known as the SCIG, it's similar to the fixed technologies. We use the squirrel cage induction generator, so we have a gearbox, but instead of connect direct the generator to the grid, we have a power converter in such a way that the power converter can guarantee the variable speed of the system done at high efficiency. The advantage is the robust generator and cheaper. The generator is very efficient, it's cheaper, it's very robust, but use a gearbox. The gearbox has the problems of maintenance. Other problem of this technology, not a problem, but a drawback. A drawback of this technology, the power converter is oversized, while the doubly fed induction generator has a converter that's only 30% of the power of the machine. This SCIG, the converter, needs to have a power more than the power of the generator. Why this? Because the induction generator consumes reactive power. So it's necessary to flow through the power converter active and reactive power. If you have a machine with 5 megawatts, we flow 5 megawatts of active power energy and also part of the reactive power to supply this machine. So this means that the higher costs involved by the converter is a technology used, very commercialized mainly by Siemens, but not largely because, of course, of the cost. Yes, probably no much interest for offshore applications due to the costs. There are other technologies preferred instead of this. Now, we see the use of synchronous generators. Before we have the use of induction generators, now the use of synchronous generators. Electrically excited synchronous generators with full converter. When we say full converter, that means that all the power, all the energy passes through the converter. The generator employs a conventional generator, similar to the hydro generators, with the feed of current to the rotor. It can be gearless, and normally it's used a gearless technology, no use of gearbox. And so this is an advantage. Power converter has the same power of the machine. If you have a synchronous machine with 10 megawatts, the converter is of 10 megawatts. This technology is cheaper than this one, but more expensive than the doubly fed here. The advantage of the synchronous generator is the absence of the gearbox, so less maintenance. But the electrical excited also has the problem of brushes and slip rings that can be avoided in some technologies. And so it's a technology very used in onshore applications. Here in Brazil, we have the company Enercon, was the first one here in Brazil, and so most of our wind parks use this kind of technology. Today, the new power plants, the new wind farms are migrating to use permanent magnet synchronous generator, known as PMSG. The PMSG also use power converters, full power converter, sized in the same power of the machine. One of the technologies with higher expansion worldwide and high interest for offshore applications. In fact, this is the dominating technology for offshore applications. If we search some manufacturers, we see that for offshore applications with machines with power higher than 8 megawatts, this is the technology used. Advantages: gearless. It's possible to have to avoid the gearbox, no slip sinks, no external excitation, then a system with less maintenance, higher efficiency at higher wind speeds. Another concept possible of this the use of the PNSG is the called semi-direct drivetrain. It's a system with a gearbox, but it's a gearbox more simple, also called medium speed generators. So when we have a gearless system, the machine it's bigger, the machine it's heavy, and the cost can be very important. When you use the gearbox, we have the problem of maintenance. So the same direct technology, it's the use of a gearbox undersized, as we said this, and so we have the combination of the advantage of the gearless and of the gearbox, and so it's a system that it's used for onshore and offshore applications, also always using permanent magnetic synchronous generators. Questions about the variable speed topologies? I know that some concepts are not clear in the first time, yes, but the concept is understand the use, the kinds of generators used, and the power electronics. It's a key for the wind systems. The main difference between the wind systems and the traditional power plants, like hydro, thermal, it's the use of power electronics. So, looking to the manufacturers, we have several manufacturers. I don't know if other lectures presented these graphs for you, but I show again. Some keys. In 2021, onshore applications with the medium rated power, the average rated power capacity of the turbines was 3.5 megawatts. The rotor size around 140 meters are 58% of the new installations. The DF5G, as I said, is 50% of the market, followed by PMSG and SCIG. The big companies, the biggest companies are Vestas from Denmark, Goldwind, China, and we have a lot of the main ones: Vestas, Siemens Gamesa, GE, and by this graph, we see that most of the companies are from China. So China is a big player on this market. It's interesting to note that in Brazil, we don't have already the presence of these Chinese companies. The China market, the Chinese market is still very, they are installing lots of wind farms in China, and so these companies are entering the Europe market, and is starting to enter in the South America market. It's a tendency to have these companies here. When you look to the offshore applications, the main companies are, again, the Vestas, Goldwind, and we see here the most installed, the Seawind, also a company from China. Looking to the installations in 2021, almost 50%, 20% of the installations are in offshore. All these companies have their own technologies, but it's most of them PMSG, ESG, these technologies that I presented here. Some manufacturers sell more than one model, and it's not, it's common, for example, Vestas, it sells the double fed and also the PMSG. Others just use the PMSG, others use just the ESG, just the market share. It's very variable, and but for offshore applications, the PMSG is the dominating technology. Questions? So, the next step in our workshop here, I know that the day today was just for me. The other days was shared between 2 or 3 persons, and for me it's one day because it's the topic is very wide, yes, and I try to bring for you the basics of each part. We talked a little bit about the wind turbine and the power curves. We talked about the generators used in commercial systems. And we see that modern turbines employ power converters. And what's the power converter? The power converter is a system to convert constant voltage, amplitude, and frequency to a variable voltage, amplitude, and frequency. This of the generator side, we have voltage and amplitude, and frequency variable. Of the grid side, fixed. So, one of the challenges for offshore applications, it's the power converter. Of course, if we have here a generator, for example, of 10 megawatts with a PMSG, we need a power converter with 10 megawatts. So we have challenges in the turbine, we have challenges in the generator, and we have challenges of technologies for power converters. This picture shows us the power converters used for offshore applications. Between 3 and 10, nowadays 12 or even 15 megawatts systems. The power converters can be divided in 2 groups. the low-level voltage source converters. What means low voltage? It's voltage below 1000 volts, 1 kilovolts. And the medium voltage converters between 2 and 13 kilovolts. These voltages are according to the grid and according to the generator. In low voltage converters, we have the two-level voltage source converters or the parallel converters, parallel connection of converters. In the medium voltage, we have also two concepts. The multi-level voltage source converters, and so we have several technologies that can be applied, and modular multi-level converters. The tendency for high power offshore applications, it's the medium voltage converters. In some of my slides, we have the sources that I show some pictures here. After I will send you, I will make available the slides, and so you can take a look on those papers. Are very interesting review papers talking about the different parts, generations and converters. Let's look the basic. A two-level back-to-back converter. A two-level back-to-back converter, this is the picture. I have a grid side converter and a machine side converter. One converter, in fact, when we say power converter here, we are talking about, in fact, about two converters. One converter connected to the grid, and one converter connected to the generator. These power converters are constructed based in semiconductors. The most used semiconductor for power converters are the insulated gate bipolar transistor, known as IGBT. The IGBT are the semiconductors used for the construction of power converters. Here we see a picture of a 1200 volts, 145 amps, and here a higher power IGBT. Here we have a comparison between the IGBT and a pencil. You see that these IGBT are small, but the power converter is not so small because we have the cooling systems, we have the control systems, everything combined here, and so it's the size, it can be compared to the size of the generator. So someone is raising the hand, Anderson?
Hello, Professor. Can you hear me?
Yes.
So, regarding this part on the power converter, I've been reading some papers, and they were concerning about the aerodynamics of the whole wind farm, saying that they would provide gains on the wind speed at each wind turbine if they used different kinds of wind turbines. Wind turbine with different rotor diameter, rotor hub height, and
powers, yes.
Yeah, exactly. Even different wind types of wind turbines. with different rated powers.
Yes, yes.
This provide as I've never seen a real wind farm built with this design scope, but they state on this journal papers that would provide aerodynamic gains. But I would like to hear from you, as you were saying regarding this electro part, that you'd have to have different kinds of power converter. How would you see this kind of design scope on the
Yes.
perspective of the electro part?
This is a good discussion. This is a possibility to have systems with different sizes and even different technologies. I can have in one wind farm the DFIG and also the PMSIG. There is nothing that hinders that. Okay. Different machines and different powers mean different power converters. And the power are different, the voltage are different, the currents are different. The main problem for this kind of system, and so I don't believe very much that the investors are interested in this kind of mixing, it's because of maintenance. For example, here in Brazil, it's very common to have problems with the power converter. So the IGBTs that we see here, they are damaged, okay, and then they have to be changed, and so they have in the available a lots of IGBTs to change. But imagine if we need one IGBT for each different. It's complicated in not the technical parts, but the economical parts. Yes, because it's necessary. Of course, if you have a huge wind farm, this can be a smaller problem. But if I have some 10, 15, 100, maybe the use of the replacement parts, it's a problem. To have the same for every turbine makes the replacements, the maintenance much attractive. Clear?
Yeah, clear. Thanks.
More questions?
Does the power converter system needs to be placed on top of the tower, or can it be underground?
It depends of the technology. Albins is asking where the power converter is placed. There are some manufacturers that place the power converter in a nacelle. That means just right to the generator, and there are companies that prefer to put the converters in the bottom of the tower. There are advantages and disadvantages for each one. If I put in the nacelle, this means that we need space. I need a cooling systems there. The space is a problem in the nacelle. If I put in the tower, in the bottom of the tower, I have a problem of cabling, of connection, and so it's not defined. Each manufacturer has its own way to put the power converter. Well, this is the basic, the two-level back-to-back converter. It's widely spread for onshore application. I can say that most of the onshore applications use this kind of converter. In this kind of converter, each of these here are IGBTs. As Anderson said, I need these IGBTs. Sometimes this fails, I have to change. We see here at least 12 IGBTs for one back-to-back converter. In these IGBTs, it's a semiconductor. What means that? They works at a switch. A switch can have two states, or closed or open. Okay? So the way that the power converters works, it's switching the semiconductors. And so the control system will control the IGBTs to have connected, disconnected, closed, open. What means? Current flowing or current not flowing. Yes. In the grid side, in the generator side, we have AC voltage. Okay? AC voltage, AC current. But the way that the power converters works, it's converting the AC voltage in each side to a DC voltage in a subsystem called DC link. What's the usability of the DC link? It's exactly as the semiconductors work open or closing, they are controlled switches. In the output of each converter, we have a switching voltage. This blue one here, I will change between plus VDC, what means plus the DC link voltage, or minus the DC link voltage. Okay? So the blue curve here is the output here in the machine side or here in the converter side and on the grid side. Okay? Okay. And each one is controlled to do this, what I want to do. But for example, when I look to the grid side and also to the machine side, I need an AC voltage. This red curve here, not a switched curve as like the blue one. The blue one, it's a curve with if we do a spectral analysis, we see the behavior of this switching of the converter, of the semiconductors. These semiconductors are generally switching in frequencies of kilohertz, 2, 3, 4 kilohertz, and so high frequency. But I am interested in the low frequency, the 60 hertz, for example, of voltage for the Brazilian grid. Therefore, and the reason why this system is called two-level, because I have just two options, plus DC link or minus DC link. But again, I am interested in the 60 hertz for the grid connection. Therefore, it's necessary to use power filters to connect the converter to the grid. The objective is, in the output of the converter, I have a switched voltage, but in the grid side, I have a pure AC voltage. This is done by the power filter, normally a LCL filter, an inductor, a capacitor, and other inductor to connect the system to the grid. And so we always will see in the connection of the grid the use of a power filter here in the WFED, in the FIG. A filter here. For the PMSIG, we see a filter here. It's always necessary to have a filter to connect the converter to the grid. The objective is to filter the voltage and have the desired behavior for grid connection. Generally, in the machine side, it's not necessary a filter, because the machine behaves like a filter, as we can say like that. Harmonic fits are not needed, in fact, for the machine side. Sometimes, if I put the converter in the bottom of the tower and I need a cable to connect the converter in the top of the generator, and sometimes I need filters there, but it's not harmonic fits. It's other kind of filters, another kind of problem that I will not discuss here. I just want to show you the components of the system. The generator, the power converter. After the power converter, we have the filter. After the filter, it's also common to use transformers. I will talk about the transformers a bit later here in this presentation. So when I have offshore applications, I have machines with higher power. So I need systems with higher currents, higher voltages. So it's necessary to do different type of converters. One way to increase the power of the converter, it's instead of have only one converter, I have two converters in parallel. In this type, I also need a filter to filter the grid connection. Sometimes I need also of the generator side to make possible this parallel connection. The disadvantage of this system is higher costs. If I have two converters, I will double the price of the converter, of course. One advantage is the improved reliability, which means if one of these converters fails, I can continue to operate with partial power. This is while the other converter is not fixed, I can use just part of the power, and so it increasing the reliability of the whole system. But for offshore applications, the multi-level converters are widely spread. In this kind, the objective of the multi-level converter is to increase the voltage and the currents according increasing the power. The difference between the multi-level converter and the two-level converter is just the structure. Here we see the structure of a two-level converter. For the multi-level converter, I have more semiconductors. This is an example of a power converter that it's very used for onshore and offshore applications. It's called three-level neutral point clamped converter or NPC converter. I don't want to present details of this, but we clearly see again one converter to connect to the generator, another converter to connect to the grid. I need a power filter again, but I have more components. That means an increased complexity. The characteristic of the multi-level converter, it's previously I had a two-level converter. Two levels were possible, plus VDC, minus VDC. Here I have three states, VDC, 0, and minus VDC. Which means that I will make the voltage in the output of the converter, as you can see, better, and so smaller power filters are necessary. Also, if I have a multi-level converter, sometimes it's possible to eliminate the use of a transformer for the grid connection, because I can increase the the voltage in the output of the converter. Example here, a 9-level converter is not commercial available, but when I have more levels, I have more the output of the converter. It's similar. It's more similar to the output desired of the grid of the machine, and so multi-level converters is a tendency for using in offshore applications. Nowadays, a lot of works, of developments, it's taking advantage of another type of multi-level converter called modular multi-level converter. It's a converter much more complicated than this one. I will not show here, but it's a technology with high improvements in terms of reliability, in terms of power filters and voltage and currents for these systems. So here is the basic of the power converters. No matter the technology I have to use the modern wind energy conversion systems, use power conversions for the connection to the grid, filters, and transformers. Questions? No questions? Multi-level converters are clear for everyone? I adopt it. But again, the objective is not to understand the whole operation, but understand the components of the system. I started with the turbine. We see the gearbox can be necessary or not, the generator, the power converter, the power filter, and now we are going in direction to the grid. How the connection of the system is done. And we start now to talk about the grid integration of systems. Here we have a typical grid configuration in onshore wind farms. I have several wind energy conversion systems. Yes. The distance between the turbines can be huge. I can have kilometers of distance between them. And so I have normally in the outside, in the output of the turbine, of the converter, I have the power filter, and after the power filter, I have a transformer. The objective of this transformer is to increase the voltage of the generator, of the whole system of the converter to a higher voltage in the grid of the park. What's the advantage of using high voltage for this connection between the turbines? I decrease the losses. And so it's interesting to have a higher voltage inside the grid of the system here. Normally, medium voltage here. All these turbines are connected to another transformer or another other transformer, what we call substation. The substation takes the voltage inside the wind farm and increases even more the voltage for the connection to the power system, to the global power system of connection of this wind farm. And so we see that the energy is produced in generally low voltage. The voltage is increased for a medium voltage inside the park, and the output of the wind park is increased. The voltage is again increased for a high voltage for the external grid connection, the power system connection. Alvin?
Hi. Is there more demand for DC power output for powering, the transportation systems, because there is less loss in transmission?
Not in onshore. Onshore, not. But you see, for offshore. Okay? DC is used for offshore. Onshore, it's almost not used. I have never seen use of DC transmission inside a wind farm like that. But for offshore, we have here. I had also several wind energy conversion systems. They are connected, what we call grids of the wind farm, and I need to connect this to the shore. And so difference arise between onshore and offshore applications. All these combined, they will produce huge amount of energy, and I have to transmit this this energy from the wind farm to the land, as to the shore. And this distance can be very high. And as we have distances, important distances between the wind farm and the grid connection in the land and the shore, normally is used high voltage transmission. The first concept is used high voltage AC connection to the shore. I have here the turbines, the generators. I have the power converter, divided here in the rectifier inverter is a power converter, a transformer inside the grid. For each one, this is similar to the onshore. I have the offshore station to increase this voltage here for a high voltage AC to connect to the onshore station. Here we have a picture of this offshore station. In this offshore station, we have transformers and protection systems. And here we see several turbines. All the turbines is connected to this offshore substation. The transmission between the offshore station and the onshore station is done in AC, high voltage AC. The problem of this topology is the distance are limited. The distance feasible distances between offshore and onshore station, it's around 100 kilometers. In offshore applications, the wind farms is even far and far from the land. And so it's necessary to transmit energy for through distances more than 100 kilometers sometimes. And so arise the concept of the HVDC that Albin just asked me. The idea is the same in the generator side. We have the turbine, we have the power converter, we have the transformer. I have an offshore station, but the offshore station is connected to the onshore station through DC voltage, and generally high DC voltage, higher than 500 kilovolts. In this offshore and onshore station, of course, in this side, I have generation in AC voltage, and in the power system, it's essentially AC also. That means that the stations, they need power converters to change between AC and DC. And there are different technologies for this. Traditional line commuted converters are converters very simple, widely known. For example, here in Brazil, the connection of Itaipu hydropower plant to the state of São Paulo, it's done by a DC part of this energy it's connected by an DC line, and there it's used line commuted converters. Is a technology more traditional, more simple, simpler, but with some problems. In fact, it's increasing the use of more modern conversion stations. Here is a picture. It's again, I have an onshore station and an offshore station. Between them, I use a high voltage DC link voltage. And but in the offshore station and onshore station, use the use of multi-level converters. The MMC or modular multi-level converters it's a technology that it's gain very attention nowadays, and it's one of the main technologies to use to connect the wind farm to the shore, to the power, the main power system. And here we see the possibilities with this. I can have for example, a PMSG, the power converter. We have seen, yes, producing in AC. And so the onshore station, an AC-DC conversion, the DC connection to the shore, and the AC conversion again to connect to the power system. Another possibility, not commercialized yet, it's used directly, the output of the system is directly in DC current, in DC voltage and DC current. In this kind of connection, so I connect direct, I need the onshore, the offshore station is a DC converter that is connected directly to the land. There are different types of technologies. Always we see that it's very interesting. It's important use of power converters. Modern power systems employs power converters. This is in the generation and also for the grid connection and for the grid transmission. Well, but what's the difference between transmission in DC voltage or transmission in AC voltage? Distance. Smaller distances, the transmission in AC is more affordable. That means smaller costs. With higher distances, the transmission in DC, the costs are more attractive. In this figure, I show here 40 kilometers, but in fact, this depends a lot. And this can vary between 50 kilometers and 100 kilometers. Each case, it's different. And so the use of transmission in AC or the transmission in DC, it's depends of the distance, depends of the characteristics of the economics. I think it's economic something economic. Questions about this? It's clear this connection, guys. So just to come back here and do a small review, I am almost finished. I talked for 3 hours. I think it's enough for one day. And what I want to show you, it's a small review of here. So we saw that we have a wind turbine, that we receive the wind. Modern systems use variable rotation, which the objective is to reach the maximum power extraction, work with maximum efficiency. This efficiency to work with variable speed, this depends on the generator, and to provide this variable speed, it's necessary a power converter. The gearbox can be used or not depending on the technology of the generator. But for high efficiency, I need a power converter to provide variable voltage and frequency, providing variable rotation. So the generator is generally connected to the grid through power converters. The power converters are connected to the grid using power filters. The objective of the power filters is to give a voltage waveform as close as possible of AC voltage. In the output of the filter, we can use a transformer to increase the voltage inside the wind farm. And the grid inside the wind farm, it's generally medium voltage, and all the turbines are connected to the substation, and this substation will increase even more the voltage. The offshore case, this connection can use AC or DC, but the objective is to transmit the energy through high distances with as small as possible losses. What means efficiency? The objective is always to increase the whole efficiency of the system, the efficiency of conversion of the wind in electrical energy in the generator, and to transmit this energy with as high as possible efficiency, smaller losses. Thoughts, questions, commentaries? So, just to finish now our presentation, I leave here for you my contact. My email is victormendes@, at cpda.ufmg.br. I work at the Laboratório de Controle e Conversão de Energia. We do a lot of research wind and also photovoltaic systems. If you put in the YouTube, I have a channel there. If you put Professor Victor Mendes, you can find more videos about the wind energy systems. It's in Portuguese, okay? But it's there. I have videos with better explanations. Yes, here we had 3 hours to talk about a lot of things. There I have smaller videos with better explanation of each topic. Of course, some topics are very related to the electrical part and need some knowledge about electrical engineering. But I hope that if you want to go deep to this topic, you can access my videos. Okay. Another advertise. Yes, I am coordinator of the especialização em energias renováveis da UFMG. Is a post-graduation course in renewable energy. Okay, here I leave to you the website, our website. In the website, you can see if you are interested to do this course. We have some informations there. Also, we have some works developed for older students in renewables energies. So I invite you to access our website and to see our program, our post-graduation program. The last one, if you put in the LinkedIn, also Victor Mendes. Sometimes I made at the LinkedIn some posts about the renewable systems, and so I invite you also to follow me. I am not a guy of LinkedIn, Facebook, Instagram, YouTube, but we need it. So I have a YouTube channel and also to spread our knowledge a little bit of LinkedIn. Okay, guys?
Victor,
Yes, Paulo.
this presentation, will it be shared on the LinkedIn?
Yes. Yes,
Okay.
you make the video. You will be available. Sarah, you make the video of this lecture available, and also you send Sarah to make I try to put the slides in the shared folder, but I have no permission for that. So I will send to Sarah, and she will send to you. Okay?
Good. Thanks.
So I am available. As I said, here is my email. If you look after to the presentation and you have doubts, I am here. I am available. Again, I hope that you enjoyed the presentation. I know that it's a lot of topics, a lot of different topics, and sometimes it's very dedicated to the electrical part. Some parts are not understandable to everyone, but I hope that at least you see the overview of the whole systems. Yes, turbine, gearbox, generator, power converter, grid connection. It's important for you at least to know the function of each part in the wind energy conversion system. So see you, and on Friday I will take part of the last discussion, and thank you for the audience.
Thank you, Victor.
Thank you for the very nice talk.
Thank you, Victor.
Thank you.
Bye.